Kick off today by doing a little motion review, okay? And at this point in time, you guys have worked through the Motion 1 packet. You guys have kind of worked through the Motion 2 packet, okay? And what those two things do is they kind of get us a base knowledge of average velocity, and then they start working on getting us a base knowledge of average acceleration, okay? So what we've learned, kind of in summary, is that the equation for average velocity, okay, is V bar, means average velocity, is displacement over time. Okay, now displacement is, for the sake of what we've been kind of working on, your change in your x position. So if I'm here and then I move over here, I've moved a certain displacement. Okay, now we've done everything in one direction linearly so far. We're going to get to a point real soon where we're going to be doing displacement in the x and displacement in the y, okay, which we'll have to use vectors, but you guys are vector experts, so we're not going to have too much problem with that, okay? So average velocity, remember when we go to Billings, we can have somebody going really fast and stopping for lunch and doing a whole bunch of things, and then we can have somebody going at constant speed. As long as you get the same distance in the same amount of time, you have the same average velocity. So average velocity isn't always a good indicator of instantaneous velocity or how fast you were going at any particular point in time. It just has to do with total displacement over total time. Okay? Now, instantaneous velocity is where we kind of get into the idea of how fast you're going at a particular instant. That is really similar to what you see when you look at your speedometer in your car. If your speedometer in your car had a direction with it, we could call it a velocimeter, and it would give you instant velocity. Okay? So if it said 50 miles per hour directly north, then that would be an instantaneous velocity. Everybody seeing that? Okay? Then, we know that the instantaneous velocity is the slope of the position versus time curve. So if we have a position versus time curve that is parabolic in nature, it's hard to find the slope at any one particular point. So Motion 1 packet was dedicated to the fact that of trying to find this slope at that point. Without calculus and without a derivative, we had to go in and find the slope of 2 points around that point and use that as an approximation for the slope of that tangent line. Does that make sense? Okay? And I think to review, we know that the slope of the position versus time curve gives us our velocity. So if we can find the slope at that point in time, it would give us our instantaneous velocity at that point in time. Okay? That's just kind of review of Motion 1 packet. Now, if we move on, talking about average acceleration, now average acceleration is going to be a bar equals change in velocity over change in time, okay? Which, if we come here, it's pretty simple, because if we have a linear velocity versus time curve, which means our velocity is increasing the same amount every second, then our average acceleration should be constant, right? Okay, because we're accelerating at the same rate. Okay, so in that case, we could take our change in velocity, which in this case would be 10, and the change in time, which in this case is 10, and we would get an average acceleration of 1 meter per second or 1 meter per second squared. Okay, does that kind of make sense? Now, let's keep moving, and I'll get to here. And instantaneous acceleration is the acceleration at a particular instant. Now I think if we look at this curve right here, guys, we agreed that our velocity is going to be changing the same amount every second. Velocity is changing the same amount every second. So do we have a constant acceleration? If you have a constant acceleration, then would your instantaneous acceleration be the same as your constant acceleration? Because it's always the same, right? Okay. Now guys, this is cool. This is where we're going to be spending most of our time for the rest of the semester, dealing with problems that are undergoing constant acceleration. Okay? That's the mathematical power that we're kind of gifted with right now. And without calculus, this next one is going to be difficult. But we'll talk about it briefly here just to give you a kind of a taste of it. If our velocity versus time is not linear, that means that we are accelerating, but we're accelerating at a accelerating amount, okay? Which is hard for your brain to kind of wrap around. But if we wanted to find the instantaneous acceleration, then what we'd have to do is we'd have to find the slope of the tangent line at that point. Okay? Now, how would we go about doing that? Well, if you had calculus, you would just take the second derivative of your position versus time, or you could, without calculus, do what we did in the motion 1 packet, is you could pick 2 points around it, and you could then find the average acceleration between those 2 points, and the average acceleration between those points would be a good approximation for the instantaneous acceleration at that point. Does that kind of make sense? Yeah. Okay. Now, I wouldn't worry too much about this because we're not going to spend much time in that realm. The next, I would say, month and a half, we're going to be spending in this situation, okay, which is constant acceleration. Okay. So, just to review one last time, okay, the slope of your position versus time yields your velocity versus time, and the slope of your velocity versus time yields your acceleration versus time. Okay? And if we were to look at a situation like this, I've left some space here. If this is accelerating at a constant rate, what is your velocity versus time graph going to look like? It should be linear. Yeah, I didn't draw that very linear, but you get the idea. It should be linear. And then what would your acceleration versus time, keeping in mind that the slope of this line yields the acceleration? So what should it look like? Should it be a horizontal constant line? Okay. And if you guys see that, this leading to this leading to this, we're in a pretty good spot. Okay. So that's a review of motion that we've had done so far.